Okay guys, in this video we are going to be discussing thermochemistry. Thermochemistry involves the study of how energy is transferred during a physical or chemical reaction. For isobaric processes, that is processes where the pressure is constant, the enthalpy change is equal to the energy that's transferred as heat. That is delta H equals Q. We'll learn later that, or we'll explicitly discuss how enthalpy is, the enthalpy change for a process depends upon the conditions of temperature and pressure. Although for this first video we are going to focus on enthalpy changes under standard state conditions. For example, I'll discuss this on the next slide as well. The standard state for gases is a hypothetical state of a pure perfect gas under conditions of standard pressure. For liquids and solids, where the standard state refers to the pure substance at those standard conditions. For solutes, we use another hypothetical model of an ideal dilute solution under standard conditions, and those standard conditions are listed on this slide here. I'll point out that standard conditions are distinct from so-called standard temperature and pressure that's used in gas law problems. I believe standard temperature and pressure is 1 atmosphere pressure and 0 degrees Celsius. Standard conditions in thermochemistry, there's actually no standard temperature. So by definition, there's no standard state temperature. However, the data does need to be tabulated at a particular temperature, and that temperature is most commonly 298.15 Kelvin. Sometimes you'll see it at 273 Kelvin. But the table that you're looking at, when you're looking at your thermochemical data tables, should always specify the temperature. Now there is a standard state pressure, and in thermochemistry, that's a pressure of 1 bar or 10 to the 5th pascals. And you may have noticed on the previous slide where I wrote the delta H with the little circle in the superscript. That superscript circle denotes the standard state conditions. So the standard pressure is 1 bar. If you're talking about concentrations, sometimes we'll use molality. Standard molality is 1 mole per kilogram for an ideal dilute solution. Standard molar concentration is 1 molar. We will talk about what an ideal dilute solution is in a future chapter when we get to solutions. For now, we're going to focus on just doing enthalpy calculations for different types of problems. Just a word on the notation that's used, and then on the next slide I show a table. When you see delta H with no circle and no label, and even when you see delta H with the circle, these typically refer to extensive versions of the enthalpy change that would be measured in joules or kilojoules. However, when you see delta H paired up with a label or with the circle and a label, these are typically going to be intensive quantities. Now there's no set rule here as far as I'm aware, but that's generally what you see. When there's a label given in a circle, that's going to be an intensive quantity expressed as kilojoules per mole. When there's no label given, it's typically kilojoules, although different authors use different conventions. So you just need to be aware of what the context is and pay attention to the units. This table shows different processes, and listed on the right are the symbols that are used to represent them. So for general phase transitions, you could use the TRS label. For specific phase transitions like fusion, when you go from a solid to a liquid, you would use the FUS. Vaporization, VAP. Sublimation, if you're making a mixture, if you're solvating a solute, hydrating an ion, all sorts of different labels that you can use. Here's the enthalpy of reaction. If you're specifically looking at a combustion reaction, you could use something like this. If you're looking at a formation reaction, you would use the F subscript. All sorts of different labels that we can use. So talking about the enthalpy of reaction, it's the enthalpy change per mole of chemical reaction. And so you can use the reported enthalpy of reaction just as you would as if it were part of the stoichiometry of the thermochemical equation. So, you know, there's a relationship. This per mole here is per mole of reaction. Okay, and so if you had a certain number of moles of oxygen reacting, you could use the stoichiometry between oxygen and the reaction to convert that to an amount of heat produced under constant pressure conditions. Conceptually, we can think of the enthalpy change for a reaction as a difference between the enthalpy of the products and the enthalpy of the reactants weighted by their signed stoichiometric coefficients. So in this notation here, we're doing a sum over all of the chemical species in the reaction. We use a minus sign for the reactants. That's what I meant by a signed stoichiometric coefficient. So the coefficient for carbon monoxide would be -1. The coefficient for oxygen would be -1/2. The coefficient for CO2 would be +1. So this is a very compact way of writing the expression for calculating delta H. You may like to revert back to the products minus reactants type of approach. Notice what we have here is the absolute enthalpy. So it's the enthalpy of the final state minus the enthalpy of the initial state. While this works conceptually, it's not what you do in practice, and so we'll get to some of the practical problems in a bit. I'd like you to be familiar with two types of very important reactions. So combustion reactions. You need to know how to balance a combustion reaction. The other type, which is on the next slide, are called formation reactions. So combustion reactions are typically exothermic. They're redox reactions, right? The oxidation number of the oxygen decreases. And so that indicate if anything like that occurs, then that's indicative of a redox process. You'll typically, here's a very general combustion reaction where I've allowed the compound to contain carbon, hydrogen, oxygen, nitrogen, and sulfur. Complete combustion leads to these products: gaseous CO2, liquid water, nitrogen, and SO2 gas. I should say complete combustion under standard state conditions leads to these products. Typically, in problems, you're going to find carbon, hydrogen, and oxygen as the only components of the compound that's being burned. What I want to point out are the conventions that are used for combustion reactions in thermochemistry. First, you want to have on the reactant side only 1 mole of your compound, and then plus oxygen. These are the products, okay? And in order to balance this equation with just 1 mole, you may end up with fractions in the chemical equation, and that's okay. You need to keep those fractions. You shouldn't get rid of them, because the rule that you have only 1 mole of the compound is the primary rule. Okay, so only 1 mole of the compound, and if there's fractions in the coefficients, so be it. You should not get rid of them. And that's because when you look up enthalpies of combustion in thermodynamic tables, they're reported for 1 mole of that compound. That's the reaction that they're referring to. So we need to keep that in mind. So here we have a reaction. We're being asked to look at the combustion of glucose. So they want to know how much heat is evolved when 10 grams of glucose is burned under standard state conditions. So we'll take glucose, And what we want to do is set up the combustion reaction and balance it. So we'll have oxygen, so this should be a solid. Oxygen, and then the products are CO2 gas and H2O liquid. 1 mole of the compound being burned, and we need to modify these coefficients. Start with carbon. You got 6 carbons here on the reactant side, so you need 6 on the product side. The next one you want to do is hydrogen. You got 12, 2 there, so you need 6. And then for the oxygen, here's how you can figure it out. You've got 6 in the compound already, plus 2 times this coefficient that you're trying to find. You got 12 here, plus 6 here, so you got a total of 18. So x equals 6. Always balance the oxygen last, and if you need a fraction for that oxygen, you need a fraction. That's all there is to it. So calculate the heat involved when 10 grams of glucose is burned. We're going to need the molar mass of glucose in order to do this calculation. So I'm going to calculate that real quick. Getting 180.2 according to my calculation. And so now what we're going to do is you're going to go from grams of glucose to moles of glucose. That essentially corresponds to moles of reaction, which you can then convert to kilojoules using the given enthalpy of combustion. So 10 grams divide by the molar mass. And then we're going to multiply that by this minus 2808 kilojoules per mole. So the heat involved is minus 156 kilojoules. So 156 kilojoules of heat is evolved in this process. The value of the heat is minus 156. The minus sign means it's exothermic. Okay, so this is a fairly standard problem in thermochemistry. We'll move on to the next type of reaction that you need to know about for thermochemistry, a so-called formation reaction. Here we would be considering either a phase transition of some sort or a redox reaction between elements in their reference form. And the key feature is that it yields only 1 mole of product. And so here's 2 examples. Carbon comes in different allotropes, and the reference form of carbon for standard state conditions is graphite. So carbon diamond is formed from carbon graphite according to this reaction here. Okay, so this is an example of a phase transition that is a formation reaction. Here's a typical formation reaction where you have 1 mole of compound on the product side, and then you have different elements in their reference form. So let's see, ethanol here has carbon, hydrogen, and oxygen in it. The reference form for carbon is graphite. The reference form for hydrogen atoms is diatomic hydrogen gas. And the reference form for oxygen is diatomic oxygen gas. By reference form, I mean the most stable allotrope for that substance under standard conditions. So a pressure of 1 bar and whatever temperature that you're considering. What I've listed below here are our common reference forms for main group elements. And so you're expected to know that these diatomic gaseous forms, these are the standard state, the reference form for all of these substances here, all of these elements. For bromine, it's diatomic, but it's a liquid. For iodine, it's diatomic, but it's a solid. You probably already know that mercury metal, its reference form is liquid. Graphite for carbon. It doesn't really matter. These two, I've just thrown them in, but it's not critical that you know those ones. But the top row here and graphite, basically everybody's going to expect that you should know those. Let's see, this last point here. Oh, this is just pointing out that if you're talking about an element in its reference form, the enthalpy of formation, this delta H subscript F, the enthalpy of formation for an element in its reference form is by definition 0. Let's take oxygen, for example. If you wanted to make the formation reaction for oxygen gas, okay, you've got 1 mole of oxygen gas on the products, and then you need the reference form of oxygen on the reactants. Well, that's O2 gas. And so, by definition, since the reactants are the same as the products, the enthalpy change for that is 0. Okay, and so that's the origin of this last statement. I just want to reiterate one more time. A formation reaction has 1 mole of compound as the product, and then you have reactants in their reference form as the reactants. And if you require fractions in order to get the reaction to balance, so be it. Those fractions need to be there. You need to be able to create the formation reaction for any compound, essentially. In this next topic, we're going to be discussing Hess's law of heat summation. Because enthalpy is a state function, the enthalpy change for a chemical reaction is independent of the path. So, for example, we can consider a 2-step reaction here. So A plus B going to C plus D and then to E plus F. Or you can consider A plus B to E plus F in 1 step. Hess's law tells us that the enthalpy change for the overall reaction is just a sum of the enthalpy change for the different steps. And so you can imagine taking reaction 1 and adding it to reaction 2. You'll see that the products from the first reaction cancel with the reactants from the second step, leading to the overall reaction. And you do the exact same procedure with the delta H values. So the enthalpy of reaction for this third reaction here is just a sum of the 2 enthalpies of reactions for the individual steps. You could have 2 steps, 1 step, you could have 1,000,000 steps. Hess's law should hold true because enthalpy is a state function. Here is a practical example of Hess's law using what I call thermochemical algebra. And so let's suppose that we are interested in knowing what is the formation enthalpy for carbon monoxide gas. Okay, so you see that we've got carbon, this would be graphite, and you've got oxygen gas, and they're combining to make carbon monoxide gas. So what is the enthalpy of formation of this? Well, the trouble is you can't very easily perform this experiment. You know, always when you take graphite and burn it in oxygen, you're always going to get some CO2 being produced. Now you can completely burn the graphite that is fully combusted so that you get only CO2. And you can take pure purified carbon monoxide, and then burn that to give you carbon dioxide. But you can't perform this reaction very easily. So these two reactions have known enthalpies of reaction, and this one is unknown to us. We'd like to know what this one is. What you need to do is to come up with a way of constructing the unknown reaction in terms of the two known reactions. Okay? And I usually do this by inspection. That method usually works for simple problems. We'll see an example in a moment where it's somewhat difficult to do, but nevertheless, let's look at this one first. So the way I figure out how do I combine these two reactions to give me this reaction is I just read the reaction from left to right. So I see that I need some carbon graphite. And so I'll look to my two reactions here and see which one contains carbon graphite. It's in this reaction 2. It's labeled 2 here. Okay, I see that I've got the carbon on the correct side of the reaction. That is, I've got carbon on the reactants, which is where I want it. And I also have the correct stoichiometric coefficient. So I'm going to start by writing that reaction 1 is going to be equal to reaction 2. And that's going to give me the carbon where I want it. Then I'll look to the next species in my unknown reaction. That's oxygen in this case. Oxygen is going to be a problem for us because we see that oxygen is in more than one compound, more than one chemical reaction. So that's my indicator that I should skip over the oxygen. And I'll look to the next product, the carbon monoxide. Okay, and so then I'll ask myself, which of the reactions contains carbon monoxide? It's this reaction labeled 3, but it's on the wrong side of the reaction. I want it on the product side, and reaction 3, it's on the reactant side. So I need to turn this reaction around. You do that by multiplying by a minus sign. Since the coefficient is 1, and I want a coefficient of 1, I don't need to multiply by anything. I just multiply it by minus 1. If you take reaction 2 and combine it with the reverse of reaction 3, you will get reaction 1. Right? It'll mathematically work out to be that. Then you perform the exact same procedure on the enthalpies of reaction. So the enthalpy of reaction 1 will be the enthalpy of reaction 2 minus the enthalpy of reaction 3, which is laid out right here. Okay, so the trick to these Hess's law problems is to figure out how do I construct my unknown reaction in terms of these known reactions. Once I get that, I can perform the calculation using the same formula. And by the way, you can always check that this works, right? So you can literally carry out, manipulate the equations and show explicitly that this combination of reactions gives you that one. So before you even do the enthalpy of reaction calculation, you can prove to yourself that you got the correct equation. Here's an example. We've got 4 reactions. Reaction 1 is our unknown. It involves the formation of tungsten carbide. And then we've got a series here of reactions that are known. Combustion of tungsten, combustion of graphite, combustion of tungsten carbide. So these are all known reactions. Here's our unknown reaction. The question is, how do we build this unknown reaction 1 in terms of the known reactions? So I like to start with my first reactant, tungsten. And where do I find it in my known reactions? I see that it's in reaction 2. Right? It's on the correct side, that is, it's a reactant, but the coefficient that I want is 1, and the coefficient that I have is 2. So what I'm going to do is I'm going to multiply reaction 2 by 1/2, and that's going to give me the correct amount of tungsten. Next, we'll move on to graphite. I want 1 mole on the reactant side. Indeed, that's what I find in reaction 3. So I'm just going to add in reaction 3. We'll move over to the tungsten carbide. Here we've got 2 moles of tungsten carbide. It's on the wrong side, and it doesn't have the correct stoichiometric coefficient. So what I need to do is reverse the reaction. That'll bring the tungsten carbide to the correct side, and then I'll divide by 2 to give me the correct stoichiometric coefficient that I want. And if you carry out this set of operations on these equations, what you'll find is that, you know, this tungsten, this tungsten oxide species is going to cancel out, and you're going to cancel out the CO2s that you don't need. The oxygens are going to cancel. So it's going to work out really well such that this combination is going to give you that one. And I'll leave that as an exercise for you to try if you don't believe me. For the enthalpy calculation itself, the enthalpy of reaction for reaction 1 is going to be 1/2 the enthalpy of reaction for reaction 2 plus the enthalpy of reaction for reaction 3 minus 1/2 the enthalpy of reaction for reaction 4. So 1/2 times negative 1685.5.8 plus negative 393.5 so that should give me the correct answer. And if I did it right in my calculator, I got minus 883.4. It's very easy to make little mistakes when doing these calculations, so it's a good idea to check it twice. I'll let you check it, and if I made a mistake, please correct it. I'm going to go ahead and move on to the next problem. This one is trickier, and you'll see why. First, you have to come up with the reactions, and I've got a typo in the problem, so that makes it harder automatically. Notice here it says the hydrogenation of propane. That's incorrect. It should say the hydrogenation of propene. So we've got, for this reaction 1, let me draw it like this. There's our double bond, CH3 like that. There's our propene, hydrogenation, and then that's giving us the propane. So we'll make that C3, I believe it's H6 plus H2 So there's the gaseous reaction that we're working with. Here, I'll write it down, minus 124 kilojoules per mole, so there's the delta H. For reaction 2, they're talking about the standard reaction enthalpy for propane. For the combustion of propane. And the enthalpy of reaction for that is minus 2200 kilojoules per mole. For reaction 3, they give us the standard enthalpy of formation for water. So there's the formation reaction for water. That's minus 286 kilojoules per mole. What reaction do they want us to find? The combustion enthalpy for propene. So reaction 4 is going to be our unknown, and it's going to be C3H6 this O2 gas, CO2 gas. It should be 3. We've got a total of 6, 7, 8, 9. 9/2. So they want us to find the enthalpy of combustion for this reaction. So how do we build reaction 4 in terms of reactions 1, 2, and 3? Now this one's tricky, and if you blindly follow that that inspection procedure that I've showed you, you're going to get the wrong reaction. And the reason you're going to get the wrong reaction is because these 3 reactions, they contain, 2 of the reactions contain H2, and they also contain water. And so this is going to give you a mismatch if you try to follow that, read the reaction from left to right. You have to think a little bit harder about this reaction, about how to construct this reaction. So you've got propene here, 1 mole. Well, reaction 1 contains propene, 1 mole. So you definitely need to add in reaction 1. Okay. Now before you move on to reaction 2, adding in reaction 2, you got to note that this reaction 1 is going to be adding propane to your products. Well, you don't want propane in your products at all because this reaction doesn't contain any propane. So you've got to get rid of that propane in the products. The only way to do that is to add in reaction 2. Right? Because adding in reaction 1 puts propane in the products. Adding in reaction 2 will take the propane out because the propane's in the reactants. So you have to add reactions 1 and 2 together. Now the last thing that you are going to want to do is to balance the, if you'll notice when you add in reaction 2, that gives you all of the CO2 that you want. So that was another good thing about adding in reaction 2. Now what you really need to worry about is the water. So you need 3 moles of water, and then the reaction 2 gives you 4 moles of water. So what you really need to do is to take away 1 mole of water in the products so that you have the 3. The way to do that is to take reaction 3 and turn it around. And so if you subtract reaction 3, it will put this water in the reactant side, which is going to cancel one of the waters there. It's also going to end up canceling 1/2 of the 5 oxygens, which is going to give you 9/2 oxygen. So I'll let you guys verify that this gives you the correct answer, and then I'm going to go ahead and let you guys do the numerical calculation as well. You basically need to take, I'll write it out just so that we're clear on what you have to do. You need to carry out that calculation using these enthalpies of reaction that I've listed above. And that'll be the correct answer to this problem. Well, I'm going to show you another motif here in Hess's law, one which is pretty useful to us in terms of thermochemistry. We've got here the statement that enthalpies of reaction can be calculated from enthalpies of formation. This is beneficial because it's way easier to make tables on individual compounds than it is to make tables on reactions, because there are many, many more reactions than there are compounds. And so if we could focus on just tabulating data for individual compounds, it's going to be a lot easier for us. And so that's what we do. Here's how you make use of the enthalpies of formation in order to calculate enthalpies of reaction. So any chemical reaction can be broken down, at least conceptually, into two steps. The first step involves taking the reactants and decomposing them into the elements of their reference form. Now, you may or may not be able to do that experimentally, but it doesn't matter. This is just a conceptual approach for doing calculations. So you take your reactants and you break them down into their elements, and then you take those elements and then you recombine them to make the products. So it's a two-step process. If you look carefully, these reactions here in the first step, these are formation reactions in reverse. That is, they are minus a formation reaction. Whereas the second step is the forward direction for a formation reaction, multiplied by stoichiometric coefficients. So what we do in order to calculate the enthalpy of reaction, we simply add up the enthalpies of formation of each species that appears in the reaction, weighted by its signed stoichiometric coefficient. Okay, and so here's the formula, the compact formula for calculating the enthalpy of reaction. You take the signed stoichiometric coefficient, which is minus for reactants, multiply it by the enthalpy of formation for that species, and you add that up over all species. If you want to get rid of the signs, that is, use the unsigned stoichiometric coefficients, you can break this sum up into a products minus reactants type of equation, which you'll recall is what you used in freshman chemistry, products minus reactants. So the idea is to tabulate enthalpies of formation and use those to calculate enthalpies of reaction whenever you need a particular reaction. So here's an illustration, a simple illustration that does that. Given the enthalpy of formation for hydrogen bromide, determine the enthalpy of formation for bromide. One thing you need to note is that the enthalpy of formation for H plus is by definition 0. It's a sort of a special ion, so to speak. In fact, so the way to state that is that it's really difficult to determine the enthalpy of formation for individual ions because the ions always come together in pairs. You can never do an experiment where you have just the cation and you don't have the anion present. So what we do is we arbitrarily set the enthalpy of formation for one of the ions to be 0, and then we report the enthalpies of formation of all other ions relative to that ion. So it's kind of a numerical trick that we use. Anyway, let's work out the formation reaction for bromide here. We'd have 1 mole of bromide aqueous. And then we would have I should put a 1/2 here. And then we would have a 1/2. Oops, a 1/2 right there. Actually, I think this, if you ask me, this problem is not written up correctly. I'm going to go ahead and just move on from that. Here's one that I think will be more in line with what I had in mind. For this problem here, you want to calculate the delta H for the reaction. And so I'm going to write it out in long form what it should be. It's going to be equal to, I start with the products, for example, the H2O2. So you would take the enthalpy of formation for that. You would add to that 4 times the enthalpy of formation for the nitrogen. That is 0 by definition because that's an element in its reference form. And then you subtract off the reactants. Okay, so we look up these values on our thermodynamic table. And then you run that through your calculator. And then I'm just going to write down here the answer that they give, minus 896.3 kilojoules per mole. I think I may have figured out this problem while I was doing the other problem. Let's write out the reactions that we have. The formation reaction for hydrogen bromide would be H2 gas 1/2 plus 1/2 Br2 liquid. So they give us the formation enthalpy for hydrobromic acid, I believe. And we would also have then the formation reaction for hydrogen to hydrogen ion. And then what they want us to find is the formation enthalpy for the bromide. And so we'll take, this is H plus Br minus because it's a strong acid. So I think this is what they meant. So what you want to do, this is our unknown, and then these are our known reactions 1 and 2. So we'll call this reaction 3. So reaction 3, we need reaction 1 to give us the bromide, and then to give us the bromine. And then to get the bromide, we need, in the products, we need to just add in, we need to get rid of the hydrogen is what we need to do. So we need to subtract reaction 2, like so. And so if you carry that out explicitly, right, if we just take 1/2 H2 plus 1/2 Br2, and then subtract reaction 2, we're going to have the H plus on this side, and then the 1/2 H2 on the other side. That's going to give us the reaction that we want. I was thrown off a little bit by the fact that they gave us the hydrogen bromide, but but that works out in the end. So in order to calculate the delta H for this reaction, it would be simply minus 122 kilojoules per mole minus 0, because the enthalpy of formation of H plus is 0. Well, we've got one more topic that I wanted to look at in this video. Talking about bond enthalpies. Bond enthalpies are a way of estimating the enthalpy of reaction. So we can use the formation enthalpies that we were working with previously to explicitly calculate the delta H for a reaction. Bond enthalpies are a quick way to just simply estimate the enthalpy for a reaction. And so here's an example of what a bond enthalpy represents. So if you've got methane here and you break one of those bonds, the enthalpy of that reaction would be equal to the bond enthalpy. Okay, so the bond enthalpy is the enthalpy change associated with breaking a bond. Here are the most important rules that you want to take away from this slide. Whenever you break a chemical bond, it's an endothermic process. So breaking any bond costs energy. And when you form a bond, that's an exothermic process. Okay? So bond breaking is endothermic, bond formation is exothermic, always, no exceptions. Here you can estimate the enthalpy of a reaction by adding up the bond enthalpies for all of the bonds that are broken in the reactants minus the bond enthalpies for all of the bonds that are formed in the products. Right? The minus sign, you're adding this to these bond enthalpies. That corresponds to bond forming, and it's exothermic, so it's the minus contribution to delta H. And then these are the endothermic contributions to delta H. Here's an example where we're being asked to estimate the enthalpy of combustion for methane using a table of bond enthalpies, and then they want you to compare that with the explicit calculation involving enthalpies of formation. So they want you to calculate the enthalpy of reaction twice. Once using bond enthalpies as an estimate, and the second one you want to compare that estimate to the value using the enthalpies of formation. So let's work out how to do this with the bond enthalpies. What you want to do is the following. So this is an estimate. You're going to break bonds. So it's bonds broken minus bonds formed. That's the way I remember it. So you're going to be breaking 4 carbon-hydrogen bonds. So bond enthalpy for carbon-hydrogen, and there's 4 of them that are being broken. Then you're breaking 2 oxygen-oxygen double bonds, right? Because you've got 2 oxygens, each of them has a double bond, so you're breaking up 2 oxygen double bonds. Now you want to subtract the bonds that are being formed. Well, carbon dioxide has 2 CO2 bonds, 2 carbon-oxygen double bonds. So we're going to subtract off the bond enthalpy for 2 carbon-oxygen double bonds. And then water has a single water has 2 oxygen-hydrogen bonds, and then there's 2 of them, so you're going to be breaking a total of 4 OH bonds. And so now you look to your table of average bond enthalpies, and you plug in the numbers. I'm getting minus 634.4 out of this. It'll be kilojoules per mole. That's our estimate. Let's see if it's any good. Calculate the enthalpy of formation. Starting with the products, we need the enthalpy, so this would be the enthalpy of reaction over here. And then the enthalpy of formation of our first product, the CO2 gas, plus 2 times the enthalpy of formation for the H2O gas. And then we'll subtract off the enthalpy of formation for the methane, and the enthalpy of formation of the oxygen 0, so we don't need to include that. So we've got minus 393.5 plus 2 times minus 241 minus the number for methane. I'm kind of curious myself. So I got minus 800 kilojoules per mole. And so this is going to be the correct value for the enthalpy of formation based upon the, or for the enthalpy of reaction based upon the enthalpies of formation. Again, this is our estimate. I'm satisfied with this result because it, A, predicted it was exothermic, which is good, and then it's several hundred kilojoules per mole. It's certainly an underestimation in terms of the magnitude, but it's still in the right ballpark. And so that's about the accuracy you can expect from these bond enthalpy calculations. They are truly just an estimate. And so, you know, when you have a fairly large negative number, you know, that's within a couple hundred kilojoules of the true value, that's about the best you can expect. And so if we had calculated this and it would have been a small number, say 100 kilojoules per mole, negative 100 kilojoules per mole, we really wouldn't even be certain if the reaction was endothermic or exothermic, right? But if it's a fairly large negative number, you can trust that you probably got the sign correct. Anyway, that's about the best you can do with these bond enthalpies. I'm going to start with this topic in the next video.